Recall the guiding principle. Start simple, then iteratively move toward more complex solutions. Linear models are often what is meant when referring to a simple model. However, there are simple forms of linear models like simple linear regression and far more complex ones that include splines, basis functions, regularization, and more. It is expected that you already use linear models as part of your modeling toolbox, so these materials are meant as a quick survey of some of the Python-centric tools that are available. We will start off with a quick review on where the different linear models fit and how they are related to each other. We will touch on the tools that enable the use of penalized regression frameworks like Ridge, Lasso, and the Elastic Net. As we will see, regularization is often built into the estimator itself. Then we will compare some variants of linear models, many of which are based on the gradient descent algorithm. Many of the linear models that are commonly used in data science, like linear regression, the t-test, and ANOVA, are examples of the general linear model. This is different from the more commonly used phrase generalized linear model, or GLM. If we relax the assumption that residuals can only be normally distributed and we introduce the concept of a link function, then these models can be extended into the family of GLMs. One extension further from GLMs brings us into another family of models known as generalized linear mixture models, or GLMMs. Hierarchical linear models or multi-level models are a very powerful example of these GLMMs, and they're a useful form of linear model. The linear regression class uses ordinary least squares, or OLS, for inference. Ridge CV, Lasso CV, and Elastic Net CV implement penalized regression with built-in cross-validation of the alpha parameter. Recall that the lasso will effectively reduce the dimensionality of your feature matrix. The multitask lasso is a linear model that estimates sparse coefficients for multiple regression problems jointly. For GLMs, the package stats models is useful, and for GLMMs, there are a number of examples in the PyMC3 documentation. Bayesian implementations of linear models have natural ways to regularize the models. This is a useful list of available tools, but it is a subset of what is available through sklearn and elsewhere. Stochastic gradient descent is a simple yet very effective approach to discriminative learning of linear classifiers under convex loss functions, such as support vector machines and logistic regression. The SVMs are assumed in this case to use a linear kernel. The SGD classifier implements stochastic gradient descent learning, which supports different loss functions and penalties for classification. SGD regressor is best used for regression problems with a large number of training samples. Pay attention to the loss and penalty arguments when using SGD-based linear models. There are three main variants of gradient descent. Gradient descent in sklearn and other packages are generally of the flavor stochastic gradient descent. In scikit-learn, stochastic gradient descent, or SGD, allows mini-batch learning for both online and out-of-core learning. These variants are useful for incremental learning and for datasets that are too large to fit into memory. This is an important algorithm that you will see over and over again in machine learning. This is an example of how you would compare different models from the sklearn linear model submodule. There are dozens of variants and even a few algorithms that we have not mentioned, like the perceptron and passive-aggressive models. Using a learning curve with respect to the error rate, we can quickly compare a number of different linear models along with different solvers. We see that the SGD is sensitive to different parameterizations, in this case the average flag. The perceptron model that we will discuss later in this course is the best performing, but note that it too is optimized with SGD. And these data are the familiar Avail churn dataset that we've been working with.